Hello and welcome to our 2-1 monomial rules. Today we're looking at quotient and negative powers. Go ahead and put today's date and your name in that top right hand corner. And now we will look at our objective. So it says, I am learning to apply the properties of monomial rules. So last video we talked about our product and power rules for monomials. Today we're going to look at quotient and negative powers. So if you notice down here, you can always hit pause if you need to. We're going to make our table again. We have our three columns. We have the name of the rule. We're actually going to see how the rule looks with variables. And now we have our examples. So it's very similar to what we had last time. And we'll start off with our very first one, quotient rule. So quotient means it's the answer to a division problem. Like how product is the answer to multiplication, quotient is the answer to division. There we go. Get it up just a hair. Perfect. Now it has the two steps, so if you think about your multiplying rules, they're just the opposite because we're dividing now. So we're going to divide or reduce coefficients. And now we're going to subtract exponents of same variables. There we go. And let me kind of scoot all this up just a hair. There we go. So those are our two main steps. Apparently I got to scoot the whole thing over just a little bit more because I wrote too large. There we go. So we divide or reduce our coefficients and subtract exponents of same variables. So what that rule would look like is if we have like x to the a power over x to the b power. Once again, we don't have any coefficients, so we just skip that first step, nothing in front. And now we just subtract your power, so it'll be x to the a minus b. Now our first example, we're given 27 x to the fifth over 42x. Now first things first, we got to reduce or divide these coefficients. So please use Desmos because it does a lot better with the fractions. We do not want decimals. So for these, we always want to write our answers as a fraction. So inside Desmos, hit your 27 divided by 42 and then find that fraction. So you have to hit the convert to fraction button. And it gives us 9/14. Let me write it out here that we have a little bit more space. 9/14. And that's because 3 can go to 27 9 times, 3 can go to 42 14 times, and we're good. So now we have two x's here. I have an x to the fifth on top, and I have an x to the first on the bottom. So 5 minus the 1 will give us x to the, oh, my fault. Try that again. Will give us x to the fourth. There we go. He stays on top because our x to the fifth has the larger exponent, and he's on top, so our x stays on top. We'll talk more about that here when we get to the negative exponent rule. But that's our solution. So we reduced our fraction. We reduced 27 over 42 to 19 over 14. And then we subtracted the exponents. We did 5 minus 1 and got 4. And now for our second example, we have y squared, and it's being squared all over y to the fourth. The first thing we have to do is simplify this numerator. So I'm going to raise it to the power. So there's no coefficient to worry about. So I'm going to multiply my powers. 2 times 2. To get y to the fourth over y to the fourth. Okay. Now, there's no coefficients to worry about, so we just skip that first step. And now 4 minus 4 will actually give us y to the 0 power. And we're going to hang out here because down here, when we hit the 0 power rule, we'll talk a little bit more about him and come back to him. So our next rule we're going to look at is the negative exponent rule. So negative exponents are not allowed. So negative exponents are not allowed. So if you're telling me that they're not allowed, what do we do about them? We're going to change location in the fraction. So change location in fraction. So that's the big thing we got to do, is change that location wherever it is in the fraction. Now the way that looks is if I have x to the negative a power, we look at that and we say we're not allowed to have negative exponents, so I can't have that. So we're going to have to put x over 1 like we would do for slope, and say my x to the negative a power doesn't want to be in the numerator, he actually wants to go to the denominator. And when we do that, we have to pretend like there's a 1 in front of our x there, so we leave a 1 on top, and say our x to the negative a power now becomes x to the positive a power, because I changed his location in the fraction. There we go. Let me make that box a little bit neater. There we go. So x to the positive a is now our denominator. He was the numerator, I took him to the bottom, made him a positive a then. So change location in the fraction. Now for our examples, the first one we're given is negative 5 x to the negative squared. So first thing we have to realize is like, okay, it already looks reduced, but so what's the problem? I have a negative exponent here on my x squared. So remember, we can put all terms over 1, and now my negative 5 doesn't have a negative exponent. He's a coefficient, so he's allowed to be negative. So I can leave my negative 5 on top. But my x to the negative squared has a negative exponent. So this guy's going to have to go to the bottom of our fraction. So I'm going to get x to the positive 2 now. So when my x squared goes to the bottom, he becomes positive 2. And that's our final answer, negative 5 over x squared. So he went from being in the numerator to being in the denominator. Now for our next example, we have 4k squared over 8k to the third. Okay, so when we do these, we always want to look first and reduce our coefficients because it's being divided. So we're going to say 4 divided by 8, and that's going to give us a 1/2. Long fraction bar there because I still have variables to deal with. Now at this point, if I do like I did up here and subtract my exponents, I'm going to get 2 minus 3, which is going to be k to the negative first power. Now if you look at that, we did subtract our exponents, but he is now a negative exponent, so he doesn't need to be on the top. He needs to go to the bottom. So it actually should be 1 over 2, and now our k to the negative first power goes to the bottom to become k to the positive first power. And there's another way to do this problem that I'm going to show you out to the side here that actually makes it a little bit faster to do it. So we're going to do the same thing as before. We divide our coefficients. 4 divided by 8 gives us 1/2, so long fraction bar there, 1/2. Now if you look at this and say which one has the higher exponent, k squared or my k to the third. If you say, well, k to the third is a bigger number, if you subtract bottom to top, you end up with the same answer. So if you do 3 minus 2 and say k's on the bottom with the bigger exponent, so k goes on the bottom, do 3 minus 2, you still get 1. And if you look, these two answers are the same. 1 over 2k, 1 over 2k. So as far as it goes, I like to do it this way where I just say that we're going to find the largest exponent and subtract it, so minus smaller exponent. Because I just think it's easier to do 3 minus 2 and say if 3 was with k on the bottom, k is going to be on the bottom, rather than having to move it later to get my final answer. But it's your choice, however you prefer to do it. And now our last rule we're going to look at today is our negative exponent rule. Or sorry, our zero exponent rule. So zero exponent rule is very, very simple, but we have to make sure we remember it, because zero exponent rule is that zero exponents always equal 1. And the rule for that one is if you have x to the 0 power, that actually means you have 0 x's. But because I do have an x there, it's like a hidden coefficient there in front of 1. So if I have 1 x to the 0 power, I have 0 x's, so that leaves me with just my 1 left over. So same way here, if I have 7 times x to the 0 power, well, x to the 0 power means I don't have any x's. So that could be like 7 times 1 instead. And 7 times 1 is just 7. Another way to think about that one is just to say if you have 7 to the 0 power, that means, or sorry, x to the 0 power, that means you have 0 x's, so that just leaves you with 7. And you get the same answer no matter which way you think about it. Monomials are pretty cool like that. You can think about them different ways and you still end up with the correct answer, as long as you follow the rules. Alright, so our last one, we have wk squared all over w to the 8th. So remember, first things first, we have to reduce our numerators. We have to raise it to the power. No coefficient to worry about, so now we're just going to multiply the powers, 4 times 2, and that will give us w to the 8th over w to the 8th. Now w to the 8th over w to the 8th means like if you subtract it, so we get 8 minus the 8, which gives us w to the 0 power, and like we just said, anything to the 0 power is just 1. There we go. Which now we come back up here to this one that we said we got y to the 0 power because we did 4 minus 4 and got 0, and y to the 0 power also goes to 1. So anything to the 0 power automatically goes to 1. Alright, so let's see some more examples.
So our first example has a to the 5th, b to the 8th, all over a, b to the 3rd. So, we first look, that fraction bar tells us we're dividing, so we first want to divide our coefficients. But we don't have any coefficients to divide, so we skip on to our variables and their exponents. Have an a to the 5th on top. And technically down here, if I have a 1a, that means I have a to the 1st power, just that 1's hidden. And we subtract our exponents. So we do 5 minus 1 gives us a to the 4th. And we drop down our b. Then 8 minus 3 is b to the 5th. There we go, and that's our dividing monomial. So let's look at one more. So example 2. We have 2p squared all over 3 to the 4th power. So this one has multiple steps in that we need to worry about our exponent and our division. So this is where the order of operations kicks in. We have to use our exponent before we can divide. So we're going to distribute it to everything. So it's going to be 2 to the 4th power. And then we multiply our variable p's exponent of 2 to the 4. So p is going to be 2 to the 4. And then my 3 also gets distributed, so 3 to the 4th power. Now we're just going to reduce. So 2 to the 4th power gives us 16. We drop down our p. And 2 times 4 is 8. All over 3 to the 4th power is 81. So then we look and we want to always check this last step to see if 16 over 81 can simplify. It can't, so that's our answer. That's as far as we can go. And one more for division. So our next example is 9b to the 4th, c to the 5th, all over 36b c squared. So for dividing, our first step we want to look at is divide our coefficients. And 9 over 36 won't reduce evenly because 36 can't go into 9. But it is a fraction that can reduce. And we say 9 can go into 9 one time, and 9 can go into 36 4 times. Now if you look at this step down here, I made a long fraction bar. And that's because whenever we're dividing, we always want to put our variables on the top part of the bar. So if we get the fraction 1/4, we make a long bar, and we're going to put our variables on top. So I'm going to drop down my b. And once again, that's b on the bottom here is b to the first because it's 1 there. So we're dividing, so we subtract our exponents. So 4 minus 1 is 3. I drop down my c and do 5 minus 2 is 3. And that's as far as we can go, and that's our answer. So here's an example of our 0 power. So if I have negative 3x to the 5th y over 8xy to the 7th to the 0 power. If you remember, whenever we have our power on the outside, when we have a monomial being raised to a power, it gets distributed. So everything in here gets to go to the 0 power. And because everything inside this parenthesis goes to 0 power, everything in the whole parentheses reduces down to just 1. Because the whole parentheses raised to the 0 power. So those are some of my favorite problems, because if you see a big parenthesis and it's all raised to the 0 power, you know it's automatically just going to be 1. So here's another example for our 0 power. So we have t to the 3rd, s to the 0 over t. So let's see what we know. We know that s to the 0 power is going to give us 1. And we know if they're side by side, that means they're being timed. So that's t to the 3rd times 1 over t. Now t to the 3rd times 1 just makes 1 t to the 3rd, so we don't have to show that 1 anymore. So we just write t to the 3rd over t. And now that fraction bar means we're being divided, so we need to subtract our exponent. So 3 minus, there's 1 down here, so 3 minus 1 is t squared. Another way to do this problem is just go ahead and say s to 0 power cancels out, and so you're left with t to the 3rd over t, and you end up with the same answer. Alright, our next one is no negative exponents allowed. And once again, if you look right here, it shows 2 minus 5. Ooh, grab the white out instead of the highlighter. 2 minus 5 gives us a negative 3. What that means is I have 3/8 left on the bottom, and the top simplifies to 1. So if I have 8 to the negative 3rd power, and I put it over 1, we say he doesn't want to be on the top. He wants to be on the bottom. So let's see an example of this. So example, don't remember what number we're on, so this will be example 6. We have b to the negative 3rd, c squared, over d to the negative 5th. So that fraction bar tells us we're dividing, but we look, I have b to the negative 3rd. Do I have any other b's? Nope, so he's just by himself. So now we're going to simplify and say b to the negative 3rd. We can't have a negative exponent. So if he's on the top part of the fraction, he doesn't want to be on the top. He wants to be on the bottom. So what I like to do is I like to go ahead and make my fraction bar and show them as I move it. So b to the negative 3rd doesn't want to be on top. He wants to be on the bottom, so it becomes b to the positive 3rd. Then we look at our c squared. His power is positive, so he wants to stay on the top. He wants to stay where he is. Then our last variable to look at is d. So I have d to the negative 5th. His power is negative. So he doesn't want to be on the bottom part of the fraction. He wants to change his location and go to the top. So d, and because he went to the top, is now to the positive 5th power. And that's our answer. We can't go any farther because they're all different variables.
let's look at example 7 here. So for example 7, we have 3x squared, y to the negative third, all over 12x to the sixth, y to the positive third. Alright, so remember that fraction bar tells us to divide, so we're going to divide and reduce our coefficients. So we'll do 3 over 12 in Desmos. Now 3 can go into 3 one time, 3 can go into 12 4 times. Always make that long fraction bar across there. And now, for this one, our exponents have higher ones on the bottom this time. So remember that rule we talked about before? That we're going to do larger exponent minus smaller exponent. And now, just because I have a little bit more space here, make a note that variable stays where it has a larger exponent. So the variable stay where exponent was the largest. Or larger, because there's only 2 of them. There we go. So if we look at our x's, we're going to do the larger exponent minus the smaller exponent. So my x to the sixth is bigger than my x squared. Now, because he's on the bottom, he's going to stay on the bottom. So I'm going to put x on the bottom. And then do my 6 larger exponent minus my 2, the smaller exponent. And 6 minus 2 gives me 4, so I get x to the fourth on the bottom. Now next, y to the negative third and y to the positive third. So which one's larger? The positive 3 is larger. And now we're going to say because y has the larger exponent on the bottom, y is going to stay on the bottom. And we subtract bottom to top. So we actually get 3 minus a negative 3. If you remember sign rules, 3 minus a negative 3 actually turns to 3 plus 3. So 3 plus 3 is 6. And we're good. That finishes us up. Now, if you were to do it the long way and do 2 minus 6, you get negative 4 on top, which means you have to take him to the bottom. Same way if you did negative 3 minus 3, you get negative 6, and you'd end up having to take him to the bottom to make him positive. So that's why it's just easier to subtract the larger exponent minus your smaller one, because if you notice in our final answer now, we didn't have to worry about any negative exponents. So always do larger exponent minus your smaller exponent, and put that variable wherever had the larger exponent. Now let's see another one, just kind of make sure we understand that rule. So example 8, we have 4x to the fifth y all over 16 x y to the fourth, and now it's being cubed. Now your monomial rules are one of those that you can think about it different ways. As long as you follow the rules, you'll be set. So you can do what's inside the parentheses first and divide. But sometimes if you divide first, you end up having to simplify again. So rather than having to simplify again, I always like to say I'm going to do it with my parenthesis by getting rid of that exponent first. So I'm going to raise everything in this parenthesis to the third power. So I'm going to raise 4 to the third power. So that's going to be 4 times 4 times 4, and that gives us 64. And now we multiply the exponent. So 5 times 3 gives me x to the 15th. And remember, that's y to the first. So 1 times 3 will give me y to the third. All over. And now we're going to do the same thing. We're going to do 16 to the third power. So everybody gets raised that third power. So 16 times 16 times 16, or 16 to the third power, gives me 4,096. And now x to the first. So we're going to multiply 1 times 3 and get x to the third. Now lastly, y to the fourth, so y, 4 times 3 gives me 12, so y to the 12th. Alright, so we got rid of that exponent. Now that we've gotten rid of that exponent, next thing we need to do is divide. So we're going to do 64 divided by 4,096. So put that right there in Desmos and make sure we were always write it as a fraction. We're going to get 1 over 64. So 1 over 64, long fraction bar. And now we look at our variables. Which one of the x's have the higher exponent? X on the top. So I'm going to keep x on the top part of my fraction, and now we subtract 15 minus 3 gives me 12. Same with the y's. We look at the y. Which y has the larger exponent? The y on the bottom. So y is going to stay on the bottom. And now we subtract. 12 minus 3 is 9. And we're all good. That's our final answer. So whenever we do that, we don't have to worry about any negative exponents. That helps us out. Alright, and one last one, example 9. We have 2x to the third, y to the negative third, to the negative second power. Now, once again, there's different ways to think about this one. As far as it goes, as long as we follow the right monomial rules, it's okay. If we focus first on the parentheses, there's nothing inside this one to reduce first. Like how before there was something inside there we could. 2x to the third, y to the negative third can't simplify. So we can't do anything inside the parenthesis. So now, what I'm going to do is say the problem with this parenthesis right now is I have a negative 2 here on the outside of it. So that negative square is going to give me problems. So I'm going to put the whole thing over 1 and take this whole parenthesis now to the bottom. So you're always left with a 1 on top if it's empty. And now I'm going to write my 2x cubed y to the negative third. But now it's to the positive second power. So I got rid of that negative power on the outside of that parenthesis. And now we're good to distribute. So I'm going to get 1 over. Remember, that's 2 squared. So 2 times 2 gives me 4. And now we multiply the exponents. So 3 times 2 will give me x to the sixth. Negative 3 times 2 gives me y to the negative sixth. Now, we've done all the monomial steps correctly, but one last thing we still have to do is get rid of that negative exponent. So I have a y to the negative 6 on the bottom. I don't like that negative exponent there, so I'm going to have to take him to the top. So now left on top, I'm going to have 1, and my y to the positive 6 now, because I took him to the top. My 4, x to the 6 stay on the bottom because they're all good. Their exponents are positive, which means we're set, and we're good. And that finishes up for our examples. Go ahead and start your practice work. If you have any questions or if you need any help, send me messages. Thanks.